Okay, now let's have another crazy function, the Dirichlet function. Okay, the Dirichlet function is defined on R by the following: f(x) equal to 1 if x is rational, 0 if x is irrational. Okay, so you can see that it's actually you cannot sketch the graph. You cannot sketch the graph because if you have even though over the 0 1, for example, 1 is here, 0 is here, 0 is a rational number, so it's here, 1/2 is here, quarter is here, so 3 quarters, a quarter is here. So if you try to sketch it, you will see almost all the point above the at 1, but also square 1/2 square root of 2, square root of 2 over 3, square root of 2 over 4, whatever number, they will be 0. But rational, irrational numbers are both dense, so you will see a graph, a line here, and automatic at the same moment the lines here. But actually, those are not lines; they have a lot of holes. Okay, and we have to prove that every point x in R is a point of discontinuity. This function is a horrible function. It is not continuous at any point. So we call it nowhere continuous. F is called nowhere continuous. Nowhere continuous. Well, how do we prove it? So for any x0 in R, so given any epsilon greater than 0, if you want to prove the continuity, if you want to prove the continuity, then given epsilon greater than 0, there exists a delta such that x minus x0 less than delta implies fx minus fx0 is less than epsilon, right? So that's the case. Okay, now given x0 in R, well, case 1, x0 is rational. x0 is rational, fx0 is 1. fx0 is 1. And we choose epsilon equal to 1/2. We always choose epsilon equal to 1/2. And for any delta greater than 0, x minus x0 less than delta, there is always an irrational x with let's choose this. There is always an irrational x with x minus x0 less than delta, because irrational number is the dense. Dense means any point you have another point. You have a point from the set close to it. Okay, and fx, because it's irrational, is 0. fx minus fx0 Ops value is equal to 1. It's greater than 1/2. 1/2 we choose it as epsilon we choose it as 1/2. Okay, so this is a contradiction. Right. Given epsilon, there is a delta. choose epsilon for all delta. For all delta, you can always, this is a for all. This and there is, okay? There is always an irrational x close to x0, fx, irrational fx is equal to 0. This is 0 minus 1 is negative 1, upper value is 1, greater than 1 half. So f is discontinuous at x0 in Q. Okay, this is our one case. The other case, x0 does not belong to Q. If x0 does not belong to Q, fx0 is equal to 0. It's irrational fx0 is 0. Then we again choose epsilon equal to 1/2 for all delta greater than 0. There is always a rational number x with x minus x0 less than delta. Fx in this case belong to is equal to 1. Upper value fx minus fx0 is again equal to 1 greater than 1/2. Here this time it is 1 minus 0, but with upper value it's always 1 greater than 1/2. Hence fx is discontinuous at x0, not belong to Q. Belong to Q, not belong to Q, fx. F is always discontinuous, so f is nowhere continuous. F is nowhere continuous. This is a horrible function. There's no way to sketch the graph of it, just because rational, irrational sets are both dense in the real numbers. Okay? Okay. So this is a Dirichlet function, a bad function. This Dirichlet function, we can modify it a little bit. We modify it a little bit. If we modify it a little bit, we can at least make it continuous at a certain point. Okay. We define the function f(x). If x is rational, rational is p over q in the reduced form. Irreducible representation, reduced form. Reduced form means you do not write 2 over 4. Okay, you do not write 2 over 4, you write 1 over 2. You cannot cancel from top and bottom anymore. In the reduced form, any rational number is a ratio of 2 integers, p over q. In the Dirichlet function, we directly define fx equal to 1. This time, we define it to be 1 over q. 1 over q, this denominator. If x is irrational, we still define it to be 0. Okay, so we modify the definition at rational numbers a little bit. Then we're going to say that proof f is continuous at irrational numbers and discontinuous at rational numbers. Continuous at the irrational number, discontinuous at the rational numbers. Alright, so you see here, with a small modification we get a lot of a continuous point, but still we have a lot of discontinuous point. It's not nowhere continuous, it's continuous at irrational numbers. The proof is a very smart proof. Now let's first prove it's discontinuous at rational numbers. This one is okay. So let x being r. case 1, x0 is p over q, rational. Fx0 is 1 over q, right? That's the definition, 1 over q. Then we choose, you see, we have this simply. We choose epsilon. This time epsilon cannot be 1/2. 1/2 actually is a half of the difference. Here 0, here's a 1, it's a half of the difference we choose in the middle. But this time, the difference is from 1 over q, between 1 over q and the 0. Real irrational number 1 over q, irrational number 0. So we choose it to be 2q, 1 over 2q, half of the value 1 over q. We choose this. Then for any delta greater than 0, there is always an irrational number x with x minus x0 less than delta. Again, dense, the same reason. And x is irrational, fx is equal to 0. And ops value fx minus fx0 is equal to 1 over q is greater than epsilon. You see, this part, because this is 1 over q, we choose half of 1 over q to guarantee it's strictly greater than it. This part is equal to 1, so we just multiply 1 by 1/2. You get a 1/2. The same idea. Same idea. It's because irrational numbers are dense in the number system. All right. So this is the proof, the same proof, identical proof. You only modify this epsilon a little bit because of the definition at this point, at this rational point is different. Well, for the continuous point, it is very interesting. X is irrational. X is irrational. So, given epsilon greater than 0, given epsilon greater than 0, there is an integer, a natural number actually, q, such that positive integer 1 over q is less than epsilon. 1 over q is less than epsilon. Well, that's reasonable, right? 1 over q is going to be very small if your q is sufficiently large. So always 1 over q is going to be less than epsilon. All right. Then we consider 1, 2, 3, 4 up to q minus 1. Up to q minus 1. There are finitely many rational numbers okay, so this part we need to make sure this is continuous. In the 0, 1, this part we just say 0, 1. It's not over the whole interval. 0, 1. That's my bad. This part you don't worry about the 0, 1 or not, but here I need 0, 1. Irrational part, the discontinuous part does not depend on 0, 1, but continuous part depends on 0, 1. There are finitely many rational numbers with denominator. One, 2, 3, 4, q minus 1. So you see here, 1/2. Which rational number has denominator 2? Just 1/2. 3, you have a 1/3, 2/3. 4, you actually only have 1 over 4. and 3/4. 2/4 is 1/2. It's already considered. 5, 1/5, 2/5, 3/5, 4/5. 6, 1/6. 2/6 is 1/3 considered. 3/6. Okay, 1/6, 5/6, right? So there are only finitely many rational numbers with the denominator 1, 2, 3, 4 up to q minus 1. There are only finitely many. Okay, so now choose delta greater than 0 such that this is x0 such that x minus x this does not include any rational numbers from above condition. So you have finite many rational numbers. Those rational numbers have distance. This is an irrational number. They're different. So they have distance from this rational number and irrational, from that rational number and irrational number. You have only finitely many of them. So I can find a small region so that this region does not include those finitely many points. Once it is finitely many different points, you can always exclude it. The situation will be different if you have infinitely many points, right? So we want a delta so that this delta will exclude all the rational numbers with the denominator 1, 2, 3, 4 up to q minus 1. Okay, in other words, if x minus x0 less than delta and x is rational equal to p1 over p2, then we get p2 is going to be greater than or equal to q. The denominator should be greater. It cannot be them, so it will be greater than or equal to q. Then this implies fx equal to 1 over p2 is less than or equal to 1 over q. Less than 1 over q, less than epsilon. Okay, so for the rational numbers in this interval, fx is always less than epsilon. Fx is always less than epsilon. If it's irrational, of course it's 0. If x is irrational, then fx is 0. Therefore, the fx minus fx0, fx0 is 0, is fx. This is just 0. So fx, it is either 0 or 1 over p2. 1 over p2 is less than 1 over q. It's always less than or equal to 1 over q and less than epsilon. Here, remember, we require this 1 over q less than epsilon. So over this interval, once you can have epsilon, you can find the q. From q, you can find this delta. So for epsilon, there's a delta, such that whenever x minus x0 ops value less than delta, this difference is less than epsilon. So f is continuous at x0. So it's continuous at x0. All right? This is a very smart way, a smart proof for the continuity of a function at an irrational point. It's big, you exclude those big. You only have finitely many possibilities for the bigger values. You just remove all of them, then you will have a smaller enough values. Okay? Okay. That's the proof of 3.33. And now let's see the final remark. The final remark says the composite function f compose g can be nowhere continuous, even though f is discontinuous. Only on Q, and G is discontinuous. Only at a point. Only at a point. Okay, so you see, G has just one bad point, but F has just bad point at Q. But when after you compose them, it is nowhere continuous. We just say that's possible. We don't say it's always true. This is a possible case. Possible case, we just provide the example. That will be the possible case. Okay, so you see here, this condition is the condition in the example 3.33. So definitely we're going to use that. So let f be the function in example 3.33. So f is only discontinuous on the rational points, and g of x, it is equal to 1 if x is not equal to 0, equal to 0 if x is equal to 0. Well, what does this mean? This means if it's not 0, make it 0. If it's equal to 0, it's 0. So g of x is like this. G of x is just make every non-zero number 1, and 0 is 0. So the reason 33 is different from Dirichlet function is that at rational numbers, it does not define it to be 1. It makes it small, 1 over q. It makes it very small. It's being smaller and smaller. You see here, it's always a 1. But if you draw this graph, you will see that at 1/2, it's 2. It's 1/2. At 1 is equal to 1. At a quarter, it's 1 over 4. At 3/4, it's still 1 over 4. So you will see, you don't see a lot of a point above. You always see, if it's 1 over 3, it will be 3. 2/3, 1 over 3 is here, sorry. 1 over 3 is here. 2/3 is here. And 1 over 5 and stuff. So actually, they are lower and lower. They become lower and lower. They're very close to 0. So that's why it is continuous over the irrational point. You try to sketch the graph of this function, you will see the graph will be very close to the x-axis. But that make this the function continuous. But this g just lift all close to 0.21, right? G just lift whatever positive, negative number to 1. Then G compose f is the Dirichlet function. Because whenever it's not 0, it's going to be 1, so it's a Dirichlet function. Dirichlet function is nowhere, which is nowhere continuous. Okay, so that's the final remark. So this section, we talk about continuity. In most cases, all the functions we see are continuous functions, or continuous almost everywhere. Okay? Sine function, cosine function. Later we will see the inverse trig functions, exponential functions, polynomial function, logarithmic function. They are always continuous over their domains. But still, we have some discontinuous functions, ops value function. It's not continuous at 0. And then we have this Dirichlet function. Dirichlet function is nowhere continuous. It does not it is not continuous at this point, that point, whatever point. And the especially interesting function is this example 3.33. This function is continuous at irrational point. Be careful about this example. This is a perfect exercise or perfect example in the exam. It's discontinuous at rational numbers and continuous at irrational numbers. All right. So let me see the exercise. Okay, so exercise. Try to prove 3. This is on page 79. Problem 3. Problem 4. Problem 4 is sum preserving property. Problem 6. Problem 6, you just do part A, no part B. Part B is so complex. Let's just try to understand the idea, not to prove some crazy stuff. And problem 8. Problem 8 is a very interesting property. It's very interesting. Problem 8 is very interesting. You may have such stuff in the exam. So problem 8 is very, very interesting. Try to do it. Okay, so we finished this section 3.3. Thank you.